It's small programs. This is an upper bound on the size of the program. Therefore, 2 to the minus this is a lower bound on the probability, because this is, well, no, the probability of this mutation, we said, is 2 to the minus its size in bits, right? So what is 2 to the minus this? Well, it's going to be 1 over k multiplied by log k squared. So we know the probability is greater than this for the mutation m sub k. Basically, if you look at this expression, sum over all k, the point is this converges. That is the crucial point here. Otherwise, this wouldn't be enough bits to express k. Basically, anything like this that converges will give you a way of coding k that's self-delimiting. This is the self-delimiting criterion. Self-delimiting is just saying basically that you have a probability measure that is less than or equal to 1, that something converges. And these are technical questions on how logarithmic information theory works. It works very much like probability theory, except you're taking logarithms. And how does probability work? The key point in probability theory is to see whether an infinite series converges or not. If it converges, if you know what you basically have in probability theory always is the sum of the probability of a series of events. If you sum one by one the probabilities of each of an infinite series of events, if that probability converges, only finitely many of the events will take place. And if it diverges and they're independent, then infinitely many of them will take place. This is called the Borel-Cantelli lemma, and it's the basic fact in probability theory. Okay, so anyway, in algorithmic information theory, it appears in transformed form because you're taking logarithms. Okay, so anyway, if the probability of m sub k is greater than or equal to this, the probability I defined it to be 2 to the minus size in bits, and we know that the number of bits you need is bounded by this plus c, so the probability will be greater than this, and therefore 1 over that is the expected time that it takes you to get to here at random, to try this m sub k at random. So the expected time is going to be roughly order of k times log k squared. So, how long will it take until you, just picking mutation at random, try m sub 1? Well, it's going to be this expression with k equal to 1. And then how many more tries of random mutation will it take until you then try m sub 2? Well, it's going to be this expression with k equal to 2. And then with k equal to 3, 4, up to the number of bits that you want to have right, in order to, and that'll get you, the lower bound on omega, which will get you to the fitness busy beaver of the number of those bits. So to get n bits right in the lower bound on omega, and to get to fitness busy beaver of n just at random, it suffices on the average to these many tries, random tries. And this sum is, of course, actually bounded by n to the 2 plus epsilon, which is the way you use in your article, which is actually a better way than I expressed it in my article. But anyway, this is intended for people who wouldn't get n to the 2 plus epsilon. I don't think they're going to get this either, but the point is that it's very easy to see that if you sum this, well, it's very easy to see that this is somewhere between n squared and n cubed, because basically this part is essentially constant, this part. And so if you take k equal to n, what you have really are terms which are, well, this is like the sum of k for k going from 1 to n, which we know how to do, multiplied by this term, which is essentially correct. Okay, so in other words, this is high school mathematics, it's basically. Okay, so this is how you get the result. Okay, and this supposedly says something about Darwinian evolution, and now you're saying, am I out of my mind? I mean, I'm also in a state of shock. This is how you prove that in my model Darwinian evolution works. But if you look at the proof, you say, my goodness, what the hell does this have to do, if anything, with biology? It doesn't look too obvious that there's anything here, as you're going through blow by blow the technical work of going through the proof. Now, by the way, it could actually be faster. It could be the system evolves faster than this. And that is a piece of technical work that needs to be done. I'm hoping that it's not the case, but there may be slightly more clever ways I'm hoping it never gets as fast as intelligent design, but I don't really know at this point. It looks unlikely to me, but intuitively I think that cumulative random evolution, you'd think has to be slower than intelligent design. That seems obvious, but if you take that remark and try to make it a mathematical proof, it turns out it doesn't work. So I'm embarrassed to say. It may be that, there's a 15-year-old who's going to say, of course it works, just like I went to Gödel when he was older than I am now and said, I'm 20, but I have a different approach, and that makes incompleteness obvious. So it's possible that that's the case. I'm hoping that's the case. I would like somebody to come up and say, it's obvious that this result you want to prove. Okay, but actually there is something here that does have to do with biology. So let me tell you what that is. It's sort of a general feature that sort of gets lost in these technical machinery. An absolutely crucial point in Darwin's theory, and Darwin understood this and appreciated this perfectly, is the question of missing intermediate forms. Darwin has a chapter in his, it says that the evolution works only if it's gradual. And each step, in Darwinian evolution, Maximo Sandin has a completely different theory of how evolution works, and he may be right, and I don't know how much of this would survive. But I'm analyzing the original proposal. Okay, so the original proposal to work, you have to have organisms which are very similar, but each of them is slightly more fit. They have to be very similar so that it's probable that just by chance you're going to go from one to the other with a random mutation. But they have to be more fit because biological evolution doesn't have foresight. It doesn't have a final goal. It only has local knowledge. So you have to, in order to be able to get to a very sophisticated organism, you have to have a series of organisms where the sophistication increases very gradually, but always fitter than the previous one. This is the key point of having an evolutionary history like that. And omega actually is that. Why? The whole point of omega is that it has a lot of information about the halting problem, so it has a lot of mathematical creativity in it. It's a wonderful oracle for the halting problem. But it works for programs of every possible size. You only have to add one bit. You can know omega one more bit at a time. You see, if you want to do very well in the busy beaver problem, for any n, there is an n-bit program that is the fittest, that calculates the biggest number. But as you change n, these programs may be vastly different. Because the program, the 100-bit program that calculates the biggest number, which is the busy beaver problem winner for 100-bit programs, may be completely different from the one that is the busy beaver winner for 101-bit programs. And that's a problem for biology and evolution. That's why you would have doubts that this system evolves, that there's anything better to do than exhaustive search. But when you realize that basically doing well in the busy beaver is the same as knowing good approximations to omega, then you can gradually you can add one, you can get one more bit and one more bit of omega at a time, and these are small changes. So that's how you get this evolutionary pathway consisting of organisms which are just changed slightly, so it's highly probable to try going from one to the other, and each of them is more fit. You see, that's the key point. And Darwin worried about this because he has a chapter in his book called On the Imperfection of the Fossil Record. And he hoped that those intermediate forms had existed in biological history, just that, by some mischance, they hadn't fallen into mud, the conditions hadn't been given for a fossil to be preserved. That was what Darwin was hoping. But he was worried. He was worried about the eye in particular, because he was worried that half an eye might be useless. Now, the eye doesn't seem to be a problem because, I don't know, some biologists told me there are actually 23 independent evolutions of eyes, different kinds of eyes. So it seems that actually that being able to see is so valuable that even if you see badly, it's better than not seeing. So the eye doesn't seem to be a problem. But there is a serious problem because it looks like the fossil record is pretty accurate, And actually there are a lot of missing intermediate forms. And this is a famous piece of work by Stephen Jay Gould and another, is it Eldridge? Some other biologist. And they call it punctuated equilibrium, which means that it looks like for a long time nothing much changes, and all of a sudden you get a lot of new species, very quickly, with not, if they're intermediate forms, I mean, it all shot by so fast you didn't get to see it. And this doesn't seem right, and this is one of the reasons that Gould, who always writes in a very ambiguous way, it basically says that Darwin was wrong, but he doesn't want to say it, so it's complicated. But and this is also a key point that Maximo Sandin seizes upon to say that Darwinism, in his opinion, wrong, and he thinks that the reason you get these big jump forward are due to viruses, which are making big changes. And this corresponds in my theory in a way to these very powerful algorithmic mutations. So that's why I was very thrilled to read Maximo's ideas, and I look forward to talking to him about this. So this actually has to do with a key issue. Now, in terms of algorithmic information theory itself, the way this expresses itself, people there are not interested in biology, they couldn't care less. Their fault, their problem as far as I'm concerned. The problem was this: the reason that omega is interesting in algorithmic information theory is connected to this in a way. The way you express this property there is, most